This is a question from the 2009 mock paper on moments of inertia, and the question involves a rough plane which is inclined at an angle 10 minus 1, 2, and if we draw that plane here, this is the plane, an angle, we call the angle A, and from the information they gave us, the 10 is 2, so we can draw this triangle down here, so we can work out the trigonometry separately. Tan of A is 2 over 1, which means by Pythagoras the remaining side, or the hypotenuse, must be root 5. So what we're dealing with is a disk that starts at this position here. We call this position 1, just to label it, and the disk rolls down the plane and ends up here at position 2, which is 45 meters away. Back to the question for some other details. We are told it's a rough plane, so there is no slipping, it rolls down, and the disk has a mass m and radius r. Now we're looking for its acceleration in terms of g. Okay, so what's involved here, as always, first of all, the moments of inertia formula from the maths tables for a disk, which is what we're dealing with. The moment of inertia through the centre, 0, is a half mr squared, where m is the mass of the disk and r is the radius. And the next thing we always use is the principle of conservation of energy. Let's write that as PCE for short. And the PCE says that the total energy at 1, so the total energy at position 1 equals total energy at position 2. That means that the potential energy plus kinetic at position 1 equals the potential energy plus kinetic energy at position 2. And now we just use our formulas. The potential energy of the disk at position 1 is mgh, formula for potential energy, plus the kinetic energy at position 1. Well, it starts at rest, so it's going to be 0, equals at position 2 potential energy. When you're dealing with potential energy, you always have to have a 0 height as your reference, a 0 position, and you can pick that wherever you want, and it's easier always to pick it at the lowest center of gravity. So we've got the disk at this position here, center of gravity is the center, so we'll pick that line along here as our 0 height. So this is the height 0 along here, which means that the potential energy at this position, if you take the height as the center of gravity, is 0, because it's mgh, where h is 0, plus the kinetic energy at position 2. Now, because it's rotating, but it's also moving in a linear fashion, I mean, this wheel is turning, which means you've angular kinetic energy, but it's also, at the same time as it's turning, it's moving in a straight line down the plane, so it's also got linear kinetic energy. So be careful here, there are two components to the kinetic energy. It's angular, which is a half I omega squared, is the formula for angular kinetic energy, plus your normal linear kinetic energy, which is a half it's a half mv squared. I might just give this a title here. Okay, so let's figure out what we know here. Well, it's mgh on this side, of course. Mgh is equal to a half I omega squared, and we can just fill in I directly for the disk. I is a half mr squared and omega squared. And now it's time to revisit the question briefly. We're looking for acceleration. So we really, I suppose what we're asking us for indirectly is the velocity or the speed at this position. Because if we have the speed here at position 2, the linear speed that is, and if we know the speed is 0 starting off, well, we can use the equations of motion, linear motion, to get acceleration. So we have to get things in terms of v, not in terms of omega. So this is the position in the question where we have to remind ourselves of the relationship between omega and v, linear velocity and angular velocity. V is equal to omega r, which means omega, of course, is v over r, and omega squared is going to be v squared over omega squared. So it's equal to v squared over omega, v squared over r squared plus a half v squared. And at this stage the m's can cancel all the way across, and let's just tidy them out a little bit. We've got gh on this side is equal to a half by half is a quarter, so we got r squared. Well, actually the r squared cancels as well, so we can get rid of that. So just get rid of this here. So the r squared cancels, and we just get v squared over 4 and v squared over 2. So v squared over 2. And so that's 3/4 v squared. That's gh. And we also can get h from trigonometry, because this is also, of course, the angle A, and if that's h, well, we can say that the sine of A is h over 45. So the sine of A is h over 45. Sine A equals h over 45, and sine of A we already know is, from this triangle, is 2 over root 5. So that's 2 over root 5 equals h over 45. So h is equal to 45 over root 5 by 2, which is actually 90. It's 90 over root 5. I'll just put a little box around that, separate calculation. And we can fill in h here now. So it's gh, which is 90 g over root 5. And that allows us to get v squared finally. So we've got everything we need now. So v squared is, we can divide across by 3, of course. 3 to 90 goes 30. So you got 30 multiplied across by 4, and you get 120 g over root 5. So v is 120 g over root 5. And this allows us to calculate acceleration, because now we know, if we go back to our original diagram, we know that u is 0 at this point. We know the v at this point. We know the distance s, which is 45, so we can work out acceleration. So u is 0. A is the question mark, and s is 45. So we can use v squared equals u squared plus 2as. And that's already v squared, actually, I think, from the previous step. So v squared is already that. So we've got 120 g over root 5 is equal to u squared, which is 0, plus 2as, which is 2a by 45, 120g over root 5 is equal to 98, and the 0 cancels on both sides. 3 goes into 9 3 times, 3 into 12 goes 4 times. So you've got 4g over 3 root 5. Meters per second squared. So that's part I of the question done. And just think there's another part there. The linear speed of the disk after rolling 45 meters down the plane, correct to one decimal place. So the linear speed of the disk, well, that's actually v. So we've already worked out v, and v is, so you just have to go to your v squared here and get the square root of that, and that will be your answer for part 2.